And then this year is the really competitive. And then compared to the last year, number of submission is more than twice. 27 papers are submitted, and then we performed the double-blinded review. And then each paper reviewed by the 3 or 4 papers. And then finally, we shortlisted the 4 finalists. They will present today. Okay? And then, so each finalist will present for the 18 minutes. This is the really fun. And after 5 minutes, I'll just stop the presentation. Okay. So plus we have the 3 minutes Q&A session. So that's basically the rule for the competition today. And then I give the sign, and then 5 minutes, actually 2 minutes, and then twice. Okay? And then I'll give the sign to each presenter. Okay? And then this is the order of presentation. First speaker is the Babak from the Oklahoma State University. And then are you the right to present? And then can you come out and present? Yes. If you are ready, and then you can start. Press the button. Now coming on. Yes. If you are ready, you can start.
Yes, I'm ready. So, hello, my name is Babak Farmanish. I'm a third-year PhD student at Oklahoma State University, and today I'm gonna present the research project that I got it done during my first year of the PhD program, which is about the treatment on Gaussian process regression and make it compatible to handle large non-stationary spatial data sets with exogenous variables or spatial data sets in higher dimensional spaces. So in this presentation, I will briefly introduce Gaussian process regression and its challenges. Then I will go through the literature and talk about the treatments that researchers have come up for handling these challenges. Then I will talk about our approach, which is called sparse pseudo-input low-cost propagating. And at the end, I will show you the experimental results. So first, what is Gaussian process? Gaussian process is about putting distributions over functions. So if a function f has a Gaussian process distribution with a mean function and a covariance function, then any subset, finite subset of this vector of infinite element has a normal distribution, joint normal distribution with a mean vector and a covariance matrix. And we can take this idea and apply it to the domain of regression, where we, for a given training set and a set of test locations, by assuming a functional relationship between x and y's, we can construct the joint distribution between the training and test data points and a normal distribution with zero mean and the variance covariance structure as like this. That, as you can see, it has 4 parts. The first one is the covariance between training data points. The second and third part is the covariance between training and test data points, and the last part is the covariance matrix between the test locations themselves. And then the predicted distribution can be easily obtained by conditioning y star given test locations and training data points with, again, a normal distribution. So what is important in this Gaussian process regression is constructing this covariance matrix which can be constructed each element of this matrix by a covariance function, which is a bivariate function that takes a pair of data points as input, and the output would be the, loosely speaking, similarity or covariance between these two data points. And the parameters of these covariance functions are called hyperparameter of our Gaussian process regression. And the precision of our Gaussian process regression highly depends on the values of these hyperparameters. And we estimate these values through maximizing the marginal likelihood, this function like this. And for example, here if you use a squared exponential function, we do this before and after training the hyperparameters. There are two big challenges and problems with Gaussian process regression. The first one is the scalability. It arises because the computational complexity is in order of n-cube, where n is the number of data points that we have. So it arises because we need to invert the covariance matrix here, which is in order of n-cube. And the other problem is the heterogeneity problem, that which means that the structure of the underlying function can vary in a way that even non-stationary covariance functions cannot capture this such kind of a structure. And these two issues usually happens when we want to deal with spatial data sets. We have massive data sets containing billions of data points, and the structure over the whole globe, here you can see, is not is heterogeneous. So there are different behaviors in different parts of the domain. So what are the treatments for these two issues? So we have two classes of approaches. The first one includes fast approximation methods that they treat the first problem. So they mainly come up with sparse approximation, sparse covariance matrix with many zero elements in the matrices. So they can use the sparse inversion techniques to invert the matrix when it's less costly to invert. Or we can use low-rank approximation. So we can approximate this covariance matrix by a low-rank covariance matrix, which is again less costly to invert. So and the basic idea is that if we can find a proper subtotal data in our domain of training data set, then we can approximate the covariance matrix with this kind of approximation and reduce the complexity from n squared to n times n cubed to n times m squared, where m is the size of this subset, which can be much smaller than the training data point size, the training data set that we have. But it depends, but this approximation only depends on the subset that we select. And the state-of-the-art approximation, low-rank approximation, is SVGP, sparse pseudo-input local Gaussian process that defines a set of pseudo data points in the domain of data, then approximate the low-rank covariance matrix for using these pseudo data points, and it has such a marginal likelihood function. And by maximizing this marginal likelihood, not only it estimate the hyperparameter, but also the location of these data points. And the complexity is on the order of n times the square, which is really efficient. But in order to handle both the challenges, we need to use local models. So in these local models, we decompose the domain into smaller subdomains and apply local Gaussian processes in each of these local models separately. And in this case, we can handle both heterogeneity and also computational complexity because of using these local models. But the problem is that most of these local models suffer from discontinuity on the boundaries of subdomains. And the state-of-the-art model for handling this discontinuity is domain decomposition method, or DDM, that locates some control points on the boundaries of subdomains. Then it tries to attach the local models on these boundaries. So it has several advantages. It handles computational complexity, it handles heterogeneity problem, and also it maintains the continuity of the underlying function over the domain. However, there is a challenge here. DDM is appropriate only for two-dimensional spaces. Why this is the case? Because number of subdomains, boundaries, and control points grows as we go higher in dimension, and also the type of constraints that we need to exert on the model would be complicated in higher dimensions. Let me just illustrate it to you. So for growth of number of control points, we can see for a simple scenario, if we have one-dimensional boundary, it would be 3. For two-dimensional boundary, it would be 9, and for three-dimensional, it would be 27. So it grows exponentially. And also, we have growth of number of boundaries and subdomains. So let's take these three-dimensional domains for the sake of illustration. And we have 3 scenarios to cut this domain. We can cut it from one direction, two directions, or all the 3 directions. So what happens? As the number of cuts increases, number of 2D boundary increases, number of square boundaries that we have. And also number of control points that we need to put on the boundaries also increases, and this increment is large, even in 3-dimensional space. And also we have some one-dimensional boundaries. Here you can see we have these lines on the boundary, and these lines actually are shared by more than 2 subdomains. They are here for 3-dimensional space. Some of them are shared by 4 subdomains. So with the type of constraints that we need to exert on our optimization model would be more complicated than DDM that has only 2 subdomains for each boundary. And also, to keep the size of subdomains small, here you can see the range should be between 200 and 600 so that the original local model can be efficient. So we need to cut it from various directions and make these subdomains small. So we usually need to use second or third scenario in order to use the idea of DDM. So what's the solution? Let's think simple. Let's just cut the domain only from a single direction. So let's just take the first scenario for cutting in higher dimensions. So what would be the advantage of cutting the domain from one direction? The advantage is that, so regardless of the dimension of the space, we get least number of boundaries and subdomains. If we have k cuts, we have k subdomains and k minus 1 boundaries. So we can control. We don't have any control on this, but in not very high dimensional space, we can control number of boundaries and subdomains, and also we can get rid of these complicated constraints because in this case each boundary is shared by at most 2 subdomains regardless of the space. But there is a challenge. If we want to use parallel cuts or orthogonal cuts to one of the axes of the space, the size of these subdomains would be large, so that the original GPR cannot be efficient in large subdomains. So what would be the solution? We can use fast approximation local models. So we use SPGP for local models, and so the procedure would be to cut them from one direction only. Then we use local SPGP for local models and train them, then attach them by using the DDM procedure. So using just locating control points and attaching them on these control points. So let's go through the formulation real quick. So at the end of the day, GPR mean predictor is a linear predictor. So it can be written as a multiplication of a matrix, coefficients in the matrix and observations. And given covariance structure of SPGP, mean squared prediction error can be written with this formula. So, and by restricting this matrix coefficient by the instruction in the DDM paper, we can restrict it to the form of psi times this approximated covariance matrix, and by minimizing this function with respect to psi, we can find the best unbiased predictor. This is a global optimization, not a local. But because of using optimization, we can make it localized. So we decompose the domain into subdomains, as parallel subdomains. Then for each omega, for each subdomain, we have a local approximation using SPGP covariance structure, and we add some control points on the boundaries of subdomains. So if JK is the boundary of subdomain between subdomain J and K, and after that we minimize this local local function with this restriction that local predictors should be equal to each other on the joint boundaries on these control points that we have, and the solution would follow Lagrange multipliers that it's sort of tedious and let's not talk about it here. And the important thing is that under any other kind of cutting policy, each boundary would be shared by more than two subdomains, and the optimization cannot be written like this easily, and the solution would be so hard. So we can, reduce the complexity by using only parallel cuts. So let's go to the experimental result. We have tested our model on 4 different data sets. The first 3 are real, and the last one is simulated data set. So the first one is in 2-dimensional space. So we have brought this because in order to compare the result with the result of domain decomposition method. So it has latitude, longitude, and the response to the total column ozone. And the second data set is the same data set, but we use an exogenous variable because our model can handle exogenous variables. So it has UV index as a 3rd dimension. Also, we have this data set that contains the salt oxygen in different depths of the ocean. So it has latitude, longitude, and altitude. And 5th dimensional, we have brought it to show that it works in higher dimensional spaces. And so we have 90% for training and 10% test, and this is the measurement, accuracy measurement criteria. And here's the result. So for each of the data set, we have, for each of the algorithms, we have brought the set of best results that they can obtain. So on the horizontal axis, we have thumb. On the vertical, we have error. And the curve closer to the origin would be superior than the other. So in 2D, we can see domain decomposition and our SPLK works better than SPGM, almost the same. And for the other data set, DDM cannot be compared, but SPLK always works better than SPGP. And also this is for sensitivity analysis that we can cut the domain for this synthetic data set from various directions, first direction, second direction. And here we have again MSC, and here we have subdomain and number of pseudo data points. As number of pseudo data points increases, MSC decreases regardless of the dimension that we cut, but the rate of decrement would vary for different directions. So it's a research question, what is the best direction of cut? And this is the conclusion. So we have your domain decomposition method. Because of using the decomposition method, we can reduce computational complexity and handle heterogeneity problem. We use fast approximation techniques for local models and cut the domain from just one direction. And because of using these two, we can attach local models in dimensional spaces greater than 2. And also, because of this, we can keep the continuity of the underlying regression functions for spatial data sets in higher dimensional spaces greater than 2. And that's all. Thank you.
So do we have about 4 minutes for the Q&A? And then do you have any questions?
So in the Gaussian process, nice talk, thank you. The Gaussian process, you're constraining to a Gaussian model, right? So there is a Dirichlet process that is pretty much unconstrained to type of distribution you have. So what do you think, shouldn't it be more fair that you compare your Gaussian process to something like that, which is, or even a particle filter which doesn't have any structure versus something structured like your comparison case? Is that a fair comparison?
It can be a fair comparison, but because of the literature that usually if any modification that researchers make on Gaussian process, they just compare it with other Gaussian process, modifications. They usually don't compare it, with other, analytics functions from different other areas. That's why we didn't do that. But maybe it can be, and maybe we can augment our paper based on that. Thank you for your question. And I would be happy to answer your questions again.
Any other questions?
Can you show the title of the talk, please?
Propagation.
Where in your approach addresses the non-stationary and where addresses the how to pronounce that?
Exogenous
Yes.
Okay,
Thank
so
you.
for non-stationarity, here the problem is the heterogeneity. So this means that this is one of the problems that it cannot handle this kind of a structure. So the function behaves differently in different parts of the domain. So for example, if we have parametric version, so maybe this part can be modeled with an exponential function, or maybe this part can be handled with a sine function. So this means that actually this a single covariance function with single hyperparameter cannot handle this kind of structure. Even we use non-stationary covariance matrices. So we need to decompose the domain in order to handle that. And for exogenous variables, so I mentioned that domain decomposition method can handle this heterogeneity problem and speed up the Gaussian process, as well as keep preserve the continuity of the overall of the underlying function. But it is only efficient for two-dimensional spaces. So if we have some special data sets containing additional information, like here I mentioned, so we have, for example, these Levitus data sets containing altitude as well. Or for this 3D, we have not only latitude, longitude, but a third variable UV index. So for these kinds of data set, DDM, first thing is that the code is not available. The second is that, it assumes that we just work on a two-dimensional domain, not higher dimensions. And that's why we have developed this algorithm to handle those exogenous variables or additional variables that we have.
Let's send to the speaker. So we are moving to the next speaker. Next speaker is the Hao Yan from the Georgia Tech. We are ready.
Thank you for giving me the opportunity to present here. My name is Hao Yan, and I'm a PhD student in School of Industrial and System Engineering in Georgia Tech. Today I'm going to present an adaptive framework for anomaly detection. So this is the outline of the presentation. And so we know that in many real systems, it's often very time consuming for us to do dense sampling. For example, in points-based sensing system, the low sampling frequency limits the number of the points can be used for online inspection. In the volcano detection, the low battery or bandwidth limits the number of sensors can be turned on. And and in the solar flare detection, the low transmission and processing capability limits the number of points can be transferred. Therefore, from those systems, we can see that actually it normally exists certain anomalies, but the anomalies only exist in a very sparse regions. Therefore, we can see most of the points and our sensors allocated are actually irrelevant, and only a small subset is actually important. So in this talk, we'll present an adaptive sampling strategy that can quickly locate those important anomalous regions and can further estimate this region. We will focus on the one point at a time system in which we try to decide the next sampling point intelligently based on the previous sampling result, so that we can reduce the measurement time by reducing the number of points needed. However, there are a few challenges, and the first one is the anomalous region can occur randomly, so that we may never know that in advance. The second is anomaly regions are typically sparse, which may be hard to localize. And the third one is the sensing noise normally unavoidable, so we should consider this in our sampling algorithm. So let's start with the existing sampling strategy and their limitations. So in the first part, multi-resolution grid sampling, they are trying to use the coarse grid over the entire sample space to find the important regions, and then they will do some fine grid sampling on these regions. However, we know this approach is not very flexible for complex anomalous space. In the second class, for sequential design of experiment, people are using criteria such as expected improvement to improve the overall functional fitting. However, if there is anomaly exists, the function may not be well approximated by one single Gaussian process model. In the third class, representative point methods such as minimum energy design are trying to allocate the points based on a fixed distribution. However, in our case, the anomaly distribution is often unknown in advance. Therefore, we propose an intelligent sampling strategy to quickly locate and focus on the anomalous region. And at the same time, we can achieve the functional mean and anomaly estimation. So before we start, let's look at two important concepts in adaptive sampling, which is exploration and exploitation. And we borrow this term from the active learning. So for exploration or space feeding, we are trying to allocate the point evenly over the space, so that to make sure there is no anomaly missing. However, if we only focus on the exploration, we cannot zoom in and focus on the important anomalous region. Furthermore, if we do focus sampling, we are trying to allocate the points on the anomalous region, which can provide enough details. However, in order to do that, we first need to know where is the anomaly. Furthermore, if we only do focus sampling, we may miss out the important regions for like other anomalous regions. Therefore, our algorithm is trying to bring a balance between the exploration and exploitation, so that we can find out all the potential anomaly and quickly zoom in to get enough information. So here are the procedures of our proposed algorithm, and let's look at the first part, the adaptive sampling algorithm. So on one hand, for the exploration property, we define the FNR function based on the minimum distance to the existing sampled point. And this is an example of the FNR function with 25 grid sampling points. And as you can see, FNR actually creates 16 local optimum. So by maximizing this function, we'll encourage the point put on this local optimum, which encourages the exploration. Furthermore, for the exploitation part, we define the FNR function based on the mixture distribution of the Gaussian kernel centered at each anomaly point. First, we add a uniform distribution on top of it to take consider of the undiscovered anomalies. So this is an example of this FNR function. As you can see, by maximizing this function, actually encourage the next sample point to be put close to the anomaly point, which encourages the exploitation. So in order to balance these two, we propose an unified sampling criterion, which is a multiplication of these two functions, but with a certain tuning parameter lambda. And we call this algorithm adaptive kernelized maximum distance. And we show that maximizing this function can actually bring the balance between exploration and exploitation in the following two properties. So in property 1, we show that this algorithm actually encourages exploitation. And as you can see, this is the same sample point with 25 sample points, but only the centered one is the anomaly point. And this sampling criterion can create this local optimum ring near the sample point. So that by maximizing this function, we'll encourage the next sample point to put on this ring, but with certain distance away to avoid overexploitation. Furthermore, we can compute the radius of this ring mathematically. For the second sampling property, we show that the proposed algorithm can balance the exploration and exploitation. So aside from this local optimum ring, this algorithm also creates 16 other local optimum. And the algorithm only chooses to sample on this ring if we sample the entire space up to a certain maximum distance. We are able to prove this property mathematically, and furthermore, this threshold, we can compute it. And by using this information, we can actually choose the right marker based on the desire of the anomaly set that we would pair out. So the next problem is that how can we optimize this sampling criterion? And we can maintain this GNR function on the x and grid. So the optimization will be just choose the largest of it. First, we show that this criterion actually have a very nice tensor structure. Furthermore, we show that this sampling criterion have a nice recursive structure, so that we can reduce the complexity to a constant complexity. After we get the sample point from the previous adaptive sampling algorithm, we would like to use it to update the estimation of the functional mean. And since we assume the functional mean is smooth, we can model the mean in reproducing kernel table space with certain kernel. And we know there may be anomalies exist. So that's why we are using the Huber robust basis. So for this robust kernel regression, we also propose an efficient optimization algorithm with closed form solution each iteration. And we also show this has global convergence. And after that, the residual can be computed by subtracting the mean from the data. And this residual information can be used to put input on to update the probability of each point being anomalous. And this probability can be used to update the sampling algorithm. And recall this is our sampling criterion function. And this is where we need this probability, but how can we compute it? We can compute it by doing a hypothesis test on the residual. And the p-value of this test can actually be updated to probability here. And after we got the sampling probability, the engineer may ask, what are the actually anomalous regions? And since we assume the anomalies are actually sparse, and we take advantage of sparse cluster structure that we use the sparse kernel regression to estimate the anomalous regions. We also provide an efficient optimization algorithm with a global convergence. So let's look at the simulation study, and we would like to evaluate our algorithm using simulation. So these are the generating model. We generate our data based on the smooth functional mean from these functions. And then on top of that, we add 7 randomly allocated cluster anomalies. And we also add a noise on top of that. So this is a simulated profile coupled with noise and anomalies. We compare the algorithm with 2 benchmark methods, which are the random sampling or the multi-resolution grid. So here is the result. So the red curve are the true anomalous regions. The yellow regions are the algorithm detected anomaly. And the black dots are the sampling criteria. This is the associated sampling criterion function, which the next point to put at the lightest color. And as we can see, the proposed algorithm will do fast exploration over the space, but as soon as it finds something interesting, it will quickly zoom in and focus something near them. But when it finds and it limits have enough sampling in this region, it will leave and try to explore the entire space again until it finds the next interesting area. However, for the random sampling, it only have around 10 points put in the anomalous region. And for the grid sampling, it's barely finished the dense grid of the first anomalous region. So if we increase the number of sample points to 400 points, the proposed algorithm is able to detect all 7 anomalies. However, for the random and gray sampling, it at most detects 3 of them. We further compute the 2 criteria, which is the F measure, which is quantified of the defect detection accuracy, and the exploitation ratio, which is trying to quantify our sampling algorithm, like how many percentage of the point are put in the anomalous region. And we computed over 5,000 iterations. So we can see that the proposed algorithm has the F measure consistently better than the other algorithm over the number of sample points. Furthermore, we show that the proposed algorithm can have an exploitation ratio increase much faster than the other algorithm. The reason is that we are able to quickly locate the important regions and quickly put a point there. And we also compute the sampling point at the computational time for the sampling for each point. And the proposed algorithm is actually able to achieve a similar order of computation time and can be used in real-time purposes. So let's evaluate our sampling strategy using the real case study, which is the eddy wave test system. And this is the setup of the system in which a vibration is put in onto the entire sample, and the laser vibrometer is able to pick up the vibration on each sample point. And for this system, it's actually very time-consuming to measure each point. For example, if we want to do dense sampling around 27,000 points, it may take up to 2 hours to finish the entire dense sampling. And in this case, this is a full measure sample, anomalous regions. And this is the detected anomaly using the full sampling. And as you can see, the detecting anomaly is using the full sampling is able to detect the entire anomaly. But for here, they only assume the partial sampling is available, and we are able to choose which point is available. And we would like to compare the proposed algorithm and detection accuracy with the full sampling. So this is the sampling result using 300 sample points, which is actually only 1% of the full sample point. And as you can see, the proposed algorithm is able to allocate those points in a much more organized way. Essentially, it puts much more number of sample points on the anomalous region. However, for the random sampling, it barely put more than 10 points on the anomalous region. And for the grid sampling, it's actually trying to limit and put dense sampling on somewhere else, and even doesn't start dense sampling on the anomalous. If we compare this detected anomaly using our algorithm with a full sampling algorithm, and as we can see, the difference between them are actually quite small. And however, in terms of number of sample points, they are able to use a much less number of sample points compared with a full sampling. So by doing this, we can potentially reduce the measurement time from 2 hours to 2 minutes without losing much accuracy. So in conclusion, we propose an intelligent and adaptive sampling framework for anomaly detection to try to balance the space filling, which is exploration, and focus sampling, which is exploitation. We also propose a functional mean and anomaly estimation procedures. And furthermore, we validate this methodology using both simulation and case study, and in both cases, we are able to show that we can reduce the number of sample points dramatically, so that we can reduce the measurement time also. So here are the references, and thank you for listening.
So we have around 4 minutes for the Q&A.
So how do you select the kernel, and how sensitive it is to the radius of the kernel? I mean, how fast your kernel is decaying.
Okay, so let's see. So basically, for selecting the kernel, yeah. So there are two parts. First part, how do we select the kernel to model the mean, the functional mean? That part can be simple since we have the data for the entire sampling. I mean, after enough sample point, we can use this data, try to use cross-validation to select the best kernel bandwidth to model the smooth functional mean. So that part is easy. So for the kernel size, for the anomaly, that part is a little bit challenging. It really depends on what size of your anomaly you are trying to detect. This part of information you should first keep in mind, like what are our interested anomaly size. And by using this size, you can choose your kernel for the anomaly. And we actually also give some criterion function how do we choose the kernel size. We can actually update the kernel size, especially for the anomaly, based on our sampling density. I mean, because if we have more and more number of samples, we have a much higher resolution. In this case, we can choose a much smaller kernel size, and then we propose to choose a kernel size based on proportional to the sampling density.
So, could you please re-explain what's your objective? You mentioned about anomaly detection.
Yes.
So does this mean you want to quickly detect it, or you want to localize the anomaly region? If you say you want to localize anomaly region, is there any guideline on the number of points that you need to sample, and then you decide to stop at this time point? You raise alarm saying this is the region?
Okay, yeah, that's another very good question. So basically, we need to first decide, as I mentioned, what is the anomaly size, right? We are actually interested. So based on this one, we can design the tuning parameter of our algorithm. And then another thing we need to decide is in the anomaly region, how much detail we would like. Like in the anomaly region, how dense something that you would like to apply. And so our algorithm have guarantee on the both distance about like how many number of sample points we need to obtain a certain radius, to make sure a certain radius of anomaly is not missing. That is the first part. The second part is how many number of sample points we need to make sure that we have dense enough sampling on the anomaly field. So this is actually criterion, our stopping criterion for the sampling algorithm.
So, nice presentation. One quick question. So, your algorithm performs very well when you have these blobs, right? So, think about something in like a nano manufacturing or polishing sense. When you don't get blobs, you get a scratch. So, what will happen at that point?
Yeah, that's another really good question. So basically, this question is like if we don't have an anomaly, like a round shape anomaly, but like a very long scratch anomaly, how do we do the sampling? So basically, for our case, if we directly use this algorithm, it will work up to some degree. It won't work perfectly. The reason is that we assume a Gaussian kernel, like Gaussian kernel is round shape. So it may sample the point based on the Gaussian kernel, but still it can't work. The reason is after you sample the point on the right direction, you will expand your anomaly distribution, and you will expand the distribution only along this direction. But you will have some other sample point, I mean, kind of a bandwidth of sample point along with the crack. So I mean, it will work. Okay, I would say not perfectly, but if you actually have prior information, you can design a kernel set based on your direction. That would be another solution. If you know, you're only trying to detect this type of anomaly lines, and you can define your kernel longer than this one, so that would work better. But that requires the prior information. Yes.
Yeah, is that possible to solve your problem by using, for example, edge detection method on image?
Okay. So your question is that possible to solve with using edge detection?
Yeah, because I know some of them are very fast.
Yeah, so basically, first, what you mentioned is I think it belongs to how do we estimate an anomalous region. And for edge detection, it's actually, one thing is actually required, from my knowledge, require dense sampling. So that for images it's okay. But for our case, we are kind of, you can think of a small sparse type of sample. So that in this case, if you directly use an edge detection, it may not work really well.
So let me stop here because the time is limited. Maybe you can ask after the sessions. And then let's thanks to the speaker again. So we are moving to the third speaker. The third speaker is the Murad from the Georgia Tech. And he's presenting. So we have a slide.
Yeah.
Thank you for inviting me. Today I'm very glad to present my joint work with my advisors Dr. Andy Sun and Dr. Ned Gabriel on sensor-driven condition-based maintenance and operation scheduling for power plants and electricity system. The presentation will proceed as follows. At the beginning of the presentation, I'll introduce this fundamental problem in power engineering called maintenance and scheduling, operation scheduling for the power plants. I'll show what the industry and the literature is doing for that, and hopefully by doing so, I'll be able to motivate our approach that's driven by the real-time sensor information. At the second part of this presentation, I'll introduce our model methodology. I'll show you how we can use the sensor information to get a better understanding on the failure of these generators and have a more intelligent maintenance and operation scheduling policy for the entire power network. And lastly, I'll conclude this presentation with some of the computational experiments and remarks. So perhaps the best way to start this presentation would be to understand in very basic terms what it is that we're trying to do. According to IEEE Task Force on Maintenance, there are 4 main objectives for doing the maintenance on power plants in power systems. The first objective is to minimize the unexpected failures, thinking that a single unexpected failure could lead to losses of up to $50 million for power companies. It's quite important that we detect the failures before it happens. Second is to extend the equipment life to the best extent possible, to reduce the early and unnecessary maintenance, and lastly, to minimize the effects of maintenance onto operations. And last point is quite important because there's a big coupling between the operations and the maintenance. So just to give a very quick example, you probably would not want to put a cheap generator under maintenance at a time of high demand, because if you put that generator under maintenance, you can't produce any electricity from that generator. You still need to satisfy the demands. That would be satisfied by a high-cost generator, and that would have a significant impact onto the operational problem. So you really need to consider both the operations, the complex interactions within the generators in the operations problem, as well as maintenance to come up with a sensible maintenance and operation scheduling policy. We have a number of approaches in literature, especially from a power engineering perspective. The predominant approach is what we call a periodic maintenance, where every generator is put under maintenance according to a certain frequency, usually once every year. The second approach is called reliability-based maintenance, where in order to understand when a certain generator might fail, what we do is we look at how long it took for similar generators to fail in the past, and based on their failure times, we try to drive a certain failure risk for generators that we have in the field. Note that in both of these approaches, we're trying to do maintenance on the particular generators that we have in the field, but in neither of them do we get any information from the generators themselves. So the thinking that we had was that if we can get the sensor information to learn the unit-specific properties from those generators, we can come up with a more intelligent maintenance and operation scheduling policy, given that we can incorporate that into the complex operational considerations in the power systems. And to do that, we're actually relying a little bit on the reliability engineering literature, which is looking on sensor-driven policies for either single component systems or very small systems, and is able to capture a small number of interactions due to the way they are modeled. They are modeled typically using Markovian decision processes or other stochastic means that are not very flexible to be able to capture the complex interactions that take place in the power systems due to the laws of physics, due to how the electricity behaves. So what we want to do is we want to use the sensor information, but we want to incorporate that into a flexible optimization methodology so that we can incorporate the needs of the power systems. In order to do that, we really have to understand what causes these degradations to fail. And from a maintenance perspective, what we look at is the degradation process, which is a gradual accumulation of damage and deterioration, which we cannot observe directly, but we can infer that degradation through sensory information. And the resulting signal is called a degradation signal. So here you can see a very simple example from a rotating machine in our laboratory. Here's a vibration signals for that rotating machine, and we can see that upon suitable feature extraction, we can come up with this degradation signal, which is really low when that rotating machine is new. But as the degradation occurs, the degradation signal starts to pick up that signal, and when that reaches to a failure threshold, we actually observe a physical failure of that engineering system. So our thinking is, if we can have a better understanding of the stochastic process, we can actually improve our understanding on when those engineering systems might fail. So I guess the best way to start is to see a very holistic view of what it is that we are proposing. So we have a number of generators, a number of power plants that are operating in the field. Everything you see in red is happening in real time. The real-time sensory information coming from these power plants is feeding into what we call a periodic predictive analytics phase, where we use the sensory information to understand the specific failure characteristics for those generators. That feeds into a dynamic maintenance cost function, which will feed into a fleet scheduling policy that will also include both maintenance inputs, the sensory inputs coming from the maintenance, but also the inputs that are coming from the operational side of things, including network topology and demand forecasts. And in order to show how our system works, I'll follow the path of information. So in this presentation, I'll show you how we can go from a low-level sensory information for a single generator all the way to a high-level scheduling for the operations and maintenance for an entire network. But first things first, we need to use the sensory information to come up with a reliable, accurate estimation on the remaining life distribution of these machines. To do that, we need to derive a continuous time and continuous state stochastic function, here denoted by DIT, which is the degradation signal of generator I at time t. So that's one-to-one corresponds with the picture that I've shown you before about how the engineering systems are degrading. That follows a certain parametric degradation function depending on the model of the generator and has a number of characteristics, the population degradation characteristics that will be typically known, and a number of degradation characteristics that are specific to that generator I, that are stochastic, that are not known. And what we want to do is we want to use the sensory information to have a better understanding of those parameters. And lastly, there's an inherent stochasticity of degradation. And once we have a good understanding of this signal, what we want to do is we want to understand when the signal reaches the failure threshold, or in other words, when a failure will occur. And to do that, we are using Bayesian learning. So we start with a prior distribution for those parameters theta I, and we leverage on the data that we observe in the field in real time to come up with a posterior distribution for those unit-specific parameters theta I. So we learn as we go along in real time, and then we condition on that posterior distribution to rederive the remaining life distribution of those generators. So with a better understanding of the degradation parameters, we can have a more accurate understanding of when these generators might fail. So far we've used the sensory information and come up with a remaining life distribution estimate. What we want to do right now is to derive a dynamic maintenance cost function using that improved understanding of the failure processes. To do that, we're using a traditional approach for determining the maintenance policies based on the renewal theory. So we're really looking at the competing factors. You don't want to put a certain generator under maintenance really early because you want to use the effective life of that generator to the best extent you can, but you don't want to postpone the maintenance too much because then you're increasing the risks of failure. So there's really two factors that place on, and this function is a very common function in maintenance literature to capture that interaction. But the thing that is unique to this function is that we are actually using the sensory information to update this function as we go along. So just to recapture on what we have done, we've used the sensory information. Using the sensory information, we updated the parameters for the degradation. We use that to update the probabilities of failure, which feeds directly into this maintenance cost function. So here you can see a quick example of what's happening. You can see as the component degrades, the degradation amplitude for that component starts to go up, so it can detect some sort of a degradation that's happening, so that our remaining life distribution estimate starts to get closer and closer to zero. And adaptively, the dynamic maintenance cost, which shows the expected maintenance cost versus time, the minimum of it starts to get closer and closer to zero. What it says is that I use the sensor information to understand it's getting close to the failure time, and I can detect that, and I can use that information in real time to understand, to evaluate the expected maintenance cost at each time period in the future. So far what we have done, we have been focusing on a single power plant or a single generator. What we want, we can now think that this process is happening for every power plant in the field in parallel. So in real time, we are using this number of modules, predictive analytics and dynamic maintenance for every generator in the field. What we want to do is we want to feed that dynamic maintenance cost functions that are updating in real time into an adaptive predictive maintenance framework. And we actually provide a comprehensive optimization problem for operations and maintenance scheduling, whereby we look at the maintenance schedule, we decide on how many maintenances to schedule for each generator and also the time of each maintenance, and also looking at the generation scheduler, which includes the unit commitment, that is the decision to turn on or off a certain generator at every hour, and also the generation dispatch that determines how much electricity you produce from each generator every hour. And we're trying to minimize the total operation and maintenance cost subject to a large number of constraints in maintenance and operations. The takeaway is that the state of the art cannot really, the formulations in the state of the art cannot really capture this sensor-driven framework. So there are a number of challenges that that cannot be answered, including the incorporation of the sensor information into the optimization problem, as well as allowing that the number of maintenances for each generator would be determined by the optimization problem itself. We want all these processes to be automated, to be driven by the sensor information. And that's why we need to come up with a new formulation. And here you can see a very condensed form of our formulation. We are trying to minimize both the maintenance and operational costs. So C transpose Z, here you see, is taking the discretized form of the dynamic maintenance cost functions that I've shown you before. So every time you get a new sensor information, you can update this dynamic maintenance cost, which then updates this C transpose in this problem, so that our maintenance cost is now driven by the sensor information. We also have operational costs, that's including the commitment and the dispatch cost. We look at a large number of constraints in maintenance side, for instance, including labor and material capacity, saying that you can put only 2 generators under maintenance at one point because your maintenance crew capacity only allows up to that many generators. We have coupling constraints that are simply saying that if you put a certain generator under maintenance, you cannot produce any electricity out of that generator during the time of maintenance. So that is coupling the maintenance and operations in a very, straightforward manner. And lastly, we have operational constraints that are relating to the unit commitment problem. The unit commitment problem is a very typical problem for operational planning of large power systems, and it's quite a difficult problem to solve from an optimization perspective as well, due to the large level of coupling that exists between generators and time periods, as well as the mixed integer nature of the problem. Here we can see there's a large number of couplings over generators. Well, for every time period, the available generators need to produce the demanded electricity. And we also need to ensure that the flow of electricity for every transmission line needs to be within the transmission line flow capacity. We also have couplings over time periods that are looking at ramping constraints, for instance, that are putting a limit on how much you can increase or decrease your level of production from one hour to the next. We have minimum off-down constraints that are looking at the scenario where in most generators, when you turn on a generator, you need to wait until a certain number of hours before you can turn it back off. So these are the couplings that exist due to the nature of how these generators work, and we cannot really relax them. But we need to incorporate them into our models. And we also have a number of constraints for every generator and time period as well. The idea is it's a very difficult problem to solve. It cannot be solved even for a 6-generator system. So what we did is we provided a new solution algorithm to be able to solve this problem, which decomposed the problem into 2 sections. The first being the master problem that's looking at the maintenance, and the second being the sub-problems that's looking at the operational problems. And we have a 2-stage algorithm. The first stage using the bandwidth decomposition to have an estimate on the lower bound for the operations, and then it's been strengthened by integer L-shaped cuts. And we have actually shown that this can reach to an optimal solution, a global optimal solution in finite number of steps. So I want to talk a little bit about the experiments. Here we are looking at a IEEE 118 bus problem where we are doing the maintenance and operation scheduling for 54 power plants for a 110-week maintenance period. We're doing maintenance for every week, and we're doing operations for every hour. And we're looking at a 48-week period through a rolling horizon fashion, using the degradation database, the real degradation data that we got from our laboratory. And as a benchmark, we are using the periodic maintenance policy and the reliability-based maintenance policy that I've underlined in the beginning of this presentation. So here's a part of our results. Our BM is the reliability-based maintenance policy, and APM, the adaptive predictive maintenance policy, is our proposed method. And here we can see we're looking at metrics in terms of IEEE Task Force on Maintenance recommendations. We can see the number of failures goes down from 13.7 and 12.2 all the way to 1.9. Showing that using sensor information, we can understand when these generators are going to fail, and therefore do maintenance before the failure actually happens. The number of total outages also goes down from 37.7 and 5 all the way to 27.6, saying that using the sensor information, we can minimize the number of unnecessary maintenances and early maintenances, and ensure that the operations goes uninterrupted. The unused life is the time difference between when you put the generator under maintenance and how long it would have taken for that generator to fail. The smaller this unused life is, the more effectively you use the equipment lifetime, in other words. And we can see that the unused life goes from 950 and 1,000 all the way to 295 in our model. So we use the equipment lifetime a lot more effectively. Maintenance cost improvement is more than 50%. And in terms of operations cost as well, this is quite an important topic, because in power engineering, it's quite an important problem to even provide small percentages of improvements into operations, because that leads to big revenues for the power companies. So the idea is, by doing a more intelligent maintenance scheduling, we can actually provide further improvements onto operations. And therefore, we're looking at it from a maintenance perspective, and we can provide further improvements in operations, which is quite valuable for the power engineering community as well. Next, we want to look at what happens when we change the frequency of updates. So the results that I've shown you before, we're actually looking at what happens when we update our maintenance every 8 weeks. We want to see what happens if that frequency increases to 6 weeks, 4 weeks, or 2 weeks. What happens is that we start to use more of the sensor information before we need to make a maintenance or optimization or operation scheduling decisions. Therefore, we can improve all the metrics that were suggested by the IEEE Task Force on Maintenance by increasing the frequency. So as a conclusion, we actually provided a sensor-driven generation maintenance and operation scheduling framework composed of 3 modules: predictive analytics, dynamic maintenance, cost analysis, and a node optimization model for operations and maintenance scheduling for an entire fleet of networks. Our framework is using the sensor information, but deriving an optimization model which is very flexible to be able to capture many different requirements that would be necessary for a power system operation. And we actually significantly improve the maintenance objectives suggested by IEEE Task Force on Maintenance. Thank you very much, and I'll be happy to answer any questions.
So, any questions from the audience? Yes.
In your optimization model for the total cost, could you explain how you consider the time period that is considered in this model? So do you consider infinite time, or you consider only a limited time period?
So for instance, in our computation model, we looked at a 110-week period. Within that 110-week period, you can do up to 3 maintenances. So this Z is a binary variable that's telling you when each maintenance takes place. So we're looking at a 110-week period, which is more than 2 years. And we're deciding on when to do maintenance based on the operations and the sensor information. So
quick question on the sensor part, the first part. So you're assuming I would say, one single sensor, right?
yes.
But in in systems, they usually use heterogeneous sensor, not one sensor,
Yes.
but different types of sensors.
Mm-hmm.
So can your modeling framework do that compressive sensing on this?
Absolutely. So this is actually showing some sort of showing that the system works. But really, you can use sensor fusion to be able to use the data to get a new estimate. as long as you can use the new data coming from thousands of signals in a power plant to have a new estimate on when that power plant might fail, you can always update your failure probabilities, and you can fit that into this model.
How do you fuse it though?
So you can either fuse it by using factors like PCA. You can use functional PCA. The thing is, this is a bit outside the area of research that I'm working on. So I'm capitalizing on the fact that people, successful researchers like Charlie, that's sitting right next to you actually, is doing sensor fusion analysis to be able to use thousands of sensors together to be able to come up with a failure probability. And as long as you can do that, you can use this model. Yes.
The maintenance optimization is dependent on the previous predictive analytics, right? So that model, for example, the sensor uncertainty and the modeling uncertainty, that will affect when the trigger is it's being triggered, right?
Yeah.
So how would that affect the following maintenance decision making?
So the uncertainty that happens in the prediction phase is actually feeding into our remaining life distribution. And the remaining life distribution feeds into the maintenance cost function itself. So if you are very certain, what happens is that you get a maintenance cost function that's really steep. If you have too much uncertainty, then you're getting a dynamic maintenance cost function that's not as steep, that provides more space for the optimization problem to further investigate whether it can move the maintenance cost solution from the optimal solution back, postponing or making it a little bit faster, maintenance itself. So that uncertainty is reflected onto the remaining life distribution. That is directly reflected onto the maintenance cost function. So it's inherently considered. Yes.
Quick question. So when you do a Bayesian updating, are you using a conjugate prior distributions?
Say it again.
Did you use a conjugate prior distribution?
Yes. I mean, because for the actual vibration signal that we use, we can do that. But again, referring to the fact that this is a proof of concept that you can use any type of prior, you can assume any prior distribution, and you can simulation methods to be able to come up with a new posterior distribution.
If you use MCMC, it's going to affect your optimization procedure, definitely.
It's not, so the thing is, it's not going to affect the procedure itself.
Again, not procedure, results.
The results it would affect, of course. So this is the proof of concept using the vibration signals coming from a rotating machinery. It would definitely affect the results. The better you estimate the distribution of these generators using the sensor information, the better you can get the results. But it would not affect the procedure of how I'm doing this.
So because of the time limitation, maybe we stop here for this presenter. So let's thanks to the speaker again. The last speaker is from the Georgia Tech, is from the Simon Mack.
Good afternoon, everyone. This is the last talk of the day, so I'm gonna try and jokes there. So I'm gonna try and include a few comics here and there, and just try and talk briefly about work that I'm working on with Professor Roshan, which is my advisor, and also my other advisor with Professor Jeff Wu. So this is a work called Support Points, which is a new way to compact distributions. This has been submitted to the annals, but it's under revision right now. So it basically talks about a way to sample from a non-normal distribution, not the right one, it's Halloween's over, but something from a normal distribution, how to optimally sample from things like that. So the name we got support points comes from the fact that we want to support this non-uniform distribution at certain points, such that the probability mass is balanced somehow. The energy of this distribution is balanced by these specific points. So because these are optimal, these provide improved performance to both Monte Carlo, which is random sampling, and quasi-Monte Carlo, which is deterministic sampling. And quasi-Monte Carlo is also restricted largely towards the uniform hypercube. So we're going to show a little bit of that later. This is very applicable for both small data and big data problems in quality and reliability. We're going to show something on uncertainty propagation for the small data and optimal reduction of big data sets for the large data. So just to sort of visually convince you why these points are good, here's 25 support points for the normal distribution, exponential, and beta. So you see that these points, the way they're allocated, they're very visually representative of the distribution. They're concentrated in areas with high density, which is exactly what you want, but they're also quite spaced out from each other, which maximizes the representability of each point. So this visual sort of representativeness leads to good performance in practice and in theory, and I'm going to illustrate that. So going to the small data problem, uncertainty propagation, what we're interested in is how uncertainties in an input, in your inputs, in an input-output process, propagate through this input-output towards your output. So here, you can imagine there's two input variables. They have beta distributions independent for their uncertainties. This can be manufacturing variability, tool wear, etc. And we want to know how this goes through the process and causes uncertainty in the output. This is a very important problem for quality improvement because we essentially want to minimize variability at the end. So the caveat here is that these experiments are very expensive to run, very time-consuming. And so what's typically performed is the bottom part, where we randomly sample a bunch of Monte Carlo samples, we take each of these input settings, dump it through the process, simulator or whatever, and then we use sample approximation to approximate the output. So if you show an engineer something like this versus this, they probably prefer the first one. First of all, it's visually appealing, and it gives you the most information from a limited number of runs, because these runs are very expensive and time-consuming. You can save money and get the most accuracy. So we plug this in the famous borehole example, which simulates water flow rate through a borehole. There's 8 uncertainties here with their distributions. And so the goal is to say, maybe you want to run 80 runs of this, sampled from this distribution, push it through the physical model, and then use the sample approximation to estimate the uncertainty in the water flow rate. So that's exactly what we did here. The middle one here is Monte Carlo. The black line is the estimated density from these 80 points. This one is the true density, the dotted line. This is for quasi-Monte Carlo, this is for our method. So we see that Monte Carlo and quasi-Monte Carlo, they do poor jobs at the peak of the distribution and at the tails, right? Using only just 80 points, we're able to nearly capture the whole output distribution quite perfectly. So this provides an improvement over state-of-the-art methods in this area. So, of course, when you're talking about all of this, and it's nice that it works, it's nice that it's visually appealing, but we also want to understand why, right? So we're going to go into a little bit of theory here. I hope you guys don't get too bored. So we're going to start off by talking about the energy distance of two distribution functions f and g, which are on some sample space script x here. If you consider x and x prime being independent copies of g, and y prime being independent copies of y, we define energy distance as this expression, where it's 2 times the expected Euclidean distance between x and y, minus the expected distance between 2 copies of x, 2 copies of g, minus that for y. And so the motivation here is that when f and g are exactly the same distribution, then the energy is 0. However, when they're different, you cannot prove that this is always positive, so it has a metric type of property. And more interestingly, when you actually replace g with an empirical distribution of points, we get this expression for the energy. And this is what Zekli and Riso proposed as a goodness of fit test, a very easy to compute goodness of fit test for testing a sample to its true distribution. This is important because the Kolmogorov-Smirnov, which is typically used, is very computationally expensive to compute. We take this one step further though, and we say, okay, let's reverse engineer this test. We want to find the best sample for a distribution f, and that's how we define support points. Right? So this is all nice and good, but we want to understand 2 basic concepts in the very least. We want to understand convergence and consistency. What we mean by convergence is we want the empirical distribution of these deterministic points to converge to the actual distribution when the number of points get very large. Right? So that's exactly what we proved here. If this is Fn is the empirical distribution for the support points, then the convergence is in distribution. So the proof of this relies on specific properties of the Fourier transform on the Euclidean norm, in which we derive the energy distance as some function of the characteristic function, and we use that to prove convergence. Second, we want to show consistency. So what we mean here is that for these points to be appropriate in integration, we want, for any integrand g, we want the sample approximation under support points to converge to the true integral under f. And that's exactly what we show here. So any continuous integrand, we get this type of consistency argument. So next, we talked about consistency convergence, but Monte Carlo has these as well. So to show that our points are better than Monte Carlo in a sense, we want to show that integration error using our points is actually faster than Monte Carlo. So to do this, we first connect the energy distance to the integration error. So if this sample space is compact, we define it, the integration error by this term of some function g. And we show that for all polynomials, this squared integration error is bounded by some function dependent on the integrand times the energy distance. So the intuition behind this is if we minimize the energy distance, we minimize the integration error for all polynomials. And in fact, this holds more than polynomials, but this is theory, right? So the goal is to try and minimize this to minimize all of the integration error. And lastly, using this result, what we can show is that support points enjoy an improved convergence rate to Monte Carlo. So there's a lot of equations or things here. Basically, what this says is the integration error is bounded by some constant times the Monte Carlo, so the 1 over square root n for Monte Carlo, times a reduction in log factors, which is an improvement over Monte Carlo. So it's better integration than Monte Carlo by polylog factor. For the specific case of the uniform distribution, QMC actually QMC is a deterministic sample, enjoys a quicker convergence rate. However, the point of all of this is not for the uniform distribution, right? For any distribution, and I'll show you that later. And in practice, our points perform much better than Monte Carlo and quasi-Monte Carlo. I'm not going to go over it. So we talked about how these things are good. Theoretically, they're good in practice. How do you optimize them? So I'm going to show that the energy distance has an appealing optimization structure, which can be used to quickly generate these points. And I'll prove that through some simulations. So the algorithm we propose is called SP.SBCD. So SP is just support points. SBCD is stochastic blockwise coordinate descent. So it minimizes the energy distance efficiently in time linear in the number of points and linear in the dimension of the space, which is both of which are very important, right? So to do this, it makes use of 3 techniques. The first one is called blockwise descent. This is typically used in variable selection, to optimize the lasso or any penalized regression. What's done here is you basically optimize the first point, fixing all of the other points, and then optimize the second point, fixing all the other points, and you cycle through everything until you get some sort of convergence. So we took this, and this will be like the blockwise optimization, which we did over B. But the problem here is the expectation is still not in closed form. So what we do is we assume F can be easily sampled. So that's an assumption. So we take a huge batch sample from F, and we just do an approximation of this blockwise problem in terms of this sample. Right. The last trick that we use is also from variable selection. This is called majorization minimization. The key of this method is when you're optimizing a function, you can always, or you're minimizing a function, you can always minimize some function which is always above it, which majorizes it, and keep on minimizing this majorization function, and you get a solution. So here, for this problem, the L2 norm is very appealing. The reason is because we can always have this type of identity. This identity is the same way of the Cauchy-Schwarz, but what this allows us to do is it allows us to majorize this using a quadratic function, which has closed form solutions, right? And so what we do is we take this, apply it to this problem. I didn't show you the actual update because it's very long, but it's an efficient closed form update for solving this approximation. And what we do here as well is we resample this batch sample every time you go through this blockwise descent. So you're always going to get some sort of convergence at the end. So applying these 3 steps together, this is the algorithm. I'm not going to go through all the steps here, but you start off with blockwise coordinate descent. For each point, you resample a huge block sample. You perform majorization minimization using this closed form update until you converge, and then you just repeat the process until your design converges. And so what we can prove is that all limiting point sets from this algorithm actually converges to some sort of stationary solution, but very efficient to what we actually want, with each update requiring linear time work in both the number of points and the dimension, which is very important. So for simulation, we tried 3 different distributions: normal, exponential, beta. We compared with Monte Carlo, which is random sampling, and quasi-Monte Carlo, which is taking the inverse of these low discrepancy sequence in QMC. We used the randomly sampled solo sequences. We tested on 2 different integrands from this test bank in 5, 10, and 50 dimensions. Now 50 dimensions is a pretty big problem, right? So we're able to, let's go through here first. So again, visually looking at these points, just for visual comparison, you would prefer support points because they're very nicely structured around the distribution, whereas Monte Carlo, well, you would expect is all over the place, right? It's not very optimal. And even the inverse quasi-Monte Carlo method is still not very structured. So this type of visual appeal actually, goes to the integration error as well. So this figure plots for each row here, we have 2 different integrants, right? And each column is the dimension, so 5, 10, 50. The black is the Monte Carlo with the error 25 and 75th quantiles, quasi-Monte Carlo with their quantiles as well. And we showed support points enjoy much lower convergence rates than both of these. And it actually improves even upon the quasi-Monte Carlo, the 25th quantile of this state-of-the-art integration method, which is quite appealing, right? And this can go into a lot of number of points as well as high dimensions. For computation time, so what this plot shows is for fixed dimension p, each of these lines are, the computation time is linear in the point set size that we want, right? Which is exactly what we proved before. And same thing with when we fix the point set and we vary the dimension, it grows linearly as well. So what this shows is that the algorithm and the method can generate moderately large point sets. I mean, I wouldn't say large, moderately large point sets in high dimensions. For example, if you want 20-dimensional point sets for this distribution, you only have to do it even for a large number of points. You only have to do a few minutes, 10, 15 minutes. And if you parallelize the whole process, you can get this down less than a minute. So this type of efficiency is very appealing. Right. So, what time are we? Okay. So, what am I to apply this? What we applied it to is an optimal way to reduce MCMC samples. So this is sort of the big data application. We talked about the small data and the uncertainty propagation. This is the big data. So we're trying to use support points to optimally reduce MCMC samples. So a little bit of context. For a lot of Bayesian problems, the posterior distribution is very complicated. And what we need to do a lot of the time is use Markov chain Monte Carlo methods, MCMC methods. One problem with all of these methods is the samples that are generated are very correlated with each other, which means we need to sample a lot of samples to get even a tiny bit of information out. And so what's done in the literature is we run these things for a very long time, and we thin the chains, which means we throw away everything except the kth sample. So if we sample 100,000, we usually thin it by 100, so we only get 1,000 samples, and we throw away everything else. This is to save storage, because to store these samples you need a lot of time, and to also reduce computations at the end. What we show here is that if you imagine this batch sample that we introduced before as the MCMC sample, right? Then we can use the same algorithm to optimally reduce MCMC chains without throwing away any samples, and you would expect better performance, right? So to show something like this, this is a project that we're working on with our aerospace collaborators at Georgia Tech, along with my advisor, Professor Jeff Wu. So here we're designing next generation rocket injectors, right? You have 5 input variables. This is a very simple case. 5 input variables for this rocket injector, and we're interested in the output, which is this spray angle, the angle right here. So there's a video. Right. So this is the simulation that's spit out by solving the Navier-Stokes coupled with a lot of different things, right? This is time, spatial temporal flow. And what we're interested in here is a bit of a simple case, just for illustration. We're interested in the time averaged angle, time average response as a function of the input space. And we're going to build an emulator using the Gaussian process as well, with the process mean, process variance, and the correlation functions, right? So that's that. So we simulate 30 different input settings from here, each of which takes a week just for this simple video. 1 week to simulate this parallels. And we're going to set this in a Bayesian setting by assigning non-informative priors. Right. Right. So we ran the MCMC after getting the data. We ran the MCMC for 250,000 samples, and then we compared the thin sample with what's produced by support points. So this figure right here shows you. So this is the process mean, process variance, right? And the black dots here, if you can see it, are actually the MCMC samples. A lot of them, right? Support points are the representative samples that we got out are the red dots. So you see visually off the top, you see support points provide a much better representation of the MCMC samples. This is because you use and this type of behavior lends well to the error as well. If you take a look at the marginal distributions as well as predictions from our emulator at 3 new settings, we're comparing thin error over support points error. And a value larger than 1 here indicates our method performs better. So you see for the marginals, for the prediction, everything performs better. So this is highly applicable not only to quality and reliability, but anywhere you use Bayesian. Right. So to summarize, support points represent are optimal representative points whenever the distribution can be easily sampled or when you already have a huge sample. Right. They perform better than Monte Carlo and quasi-Monte Carlo, both theoretically and in practice. And there are many exciting applications for support points. So we talked about uncertainty propagation, we talked about Bayesian analysis, but the same methodology can be used to manipulate and to compact big data sets, large data, right? It can be used in stochastic optimization when you're using a sample average approximation. You can use support points instead. You get better convergence rates and an experimental design. So this is a very exciting area that to think about the application as well as the theory for support points as well. So, thank you. Any questions?
Yeah, we have about 3 minutes for the questions.
So Bayesian, we have samplers, we use MCMC, but we grit our teeth with it. Like it's the most painful part to get the samples.
Yeah.
They're not easily sampled.
Yes. Yeah.
But we're throwing out a lot of the points.
Yeah.
So in a sense, could we then use this to think of better samplers, like more directed samplers? I mean, if we're really trying to improve computational effort, especially with the Gaussian process, the actual MCMC sampling is the expensive part.
Right. So there's 2 parts to your question. First of all is, when you get this huge sample, you of course want to speed up the sampling part of this. But a byproduct is when you have this huge sample, you also want to reduce this to some sort of optimal sample. The first part is actually what we're working on in the future work, is all of these rely on samples from the distribution, from the density, right? Because MCMC relies on just the unnormalized density. We're trying to combine some sort of way, and my advisor is working on this with the minimum energy design, to approximate this somehow just using the density, right? And in that sense, you can just combine it with some sort of, maybe 1 step of MCMC and then use some sort of optimization using this density function to correct it. And in that sense, because the convergence rate of this is actually faster than Monte Carlo, you can actually hit faster convergence rates, which is quite interesting. So I hope that answers. Any other questions? Any other questions?
So I have one question actually. So how the sampling is working with the multimodality? So you have a multimodality with the distributions. How
Right.
is this working?
So when you have multimodal distributions, I mean, all the method is really assuming is that this is a continuous distribution and it can be easily sampled. So once you have a method of sampling a multimodal, that goes back to the original point. You have to find some way to sample it first. Right. This is like the first step in sort of correcting the whole process. But once you have the samples, you can reduce it.
Okay. Yeah. And another question is, do you need actually the specific closed form for the density function of the you want to the sampling from? Or you need something?
So here you need samples, right? Right. I mean, but if you want to generalize this and say, so there are MCMC methods where you only want to use just the density function, which you know to a normal line. There's some where you can't compute the likelihood, but you can simulate, right? For a lot of ABC methods, approximate Bayesian methods, they can sample, but they can't compute the likelihood. So that's sort of part of your case. In this case, once you get the samples, you don't need the likelihood. And you can use that to compact.
So any other questions? So
So is it possible to use the entropy as a criteria to minimize this F and Fn?
Right. So that's actually a very interesting point. This energy criterion, it's been studied for the last 10 years, but there's a very innate, interpretation of this energy criterion in terms of, physical potential. So this sort of crosses over with like a physical, or an area called, it's lost. But anyway, so there's a very nice interpretation of this as an entropy measure as well. So in that sense, it's sort of like a minimum energy type of sampling.
Other questions?
Yeah.
So you showed one example about 50 dimension.
50, yeah.
Yeah, but for MCMC, sometimes we can easily go hundreds or thousands.
Correct.
Do you have any comments with that?
Right. So we actually tried this. The sample size shouldn't be too much of a big problem. I mean, here we actually dumped it to all the way to 100, right? Because this thing is linearly scaling in p. However, that's a problem when the point set you want to get back is also very large as well, including the dimension. But I mean, even in variable selection type of literature, when you have large n, large p, it's still a hard problem, right? Even so, I mean, we could propose some sort of sequential type of thing, and that's something that we're working on as well. To do this quickly, and you don't have to. It's probably faster than linear time. But that's definitely an interesting question.
Yeah. So if you do not have any question, we just review it today, and then so outcome will be announced tomorrow at the QSR business meeting. Okay. Thank you for coming.